All right, so we'll do a little bit of review today. So one thing I'm going to do, so this formula sheet, we kind of just start out with those matched pairs. Originally, I think I had uploaded this practice exam C, which had some of the comparing two populations. I think I'm going to try to make it a little bit easier on you guys. I want to know a little bit of stuff, I want you to still be able to do some hypothesis testing stuff. So I'm keeping that matched pairs on there. And I'm always using the student T distribution to look up p-values, to look up critical values. But you're not going to have to worry about putting any of the comparing two populations stuff, other than the matched pairs, right? So it's going to be kind of heavily on linear regression. And then how, like I mentioned on Friday, you'll have your kind of set of matched pairs questions. If you're looking at this practice or the other practice exam, maybe a few more than what's on there. And then some analysis of ANOVA, right? How do I determine if there's variation across rows or columns? But then the majority of it's going to be kind of based off this linear regression stuff we've been talking about. So I'll dive into some of the tougher stuff with that today, unless anybody has very specific questions that they want to start out covering. Anybody had looked at this as wanting a specific number?
Can you go over like what I just have?
So before I kind of jump into it, the other thing I want to mention, so I think I said this Friday, but the exam will be about 15 multiple choice questions. Maybe more, I can't remember the exact, it might be 16 or 17. I got it to work out to be a certain number of points. So right around 15, maybe one or two more, and then 4 short answer questions kind of with multiple parts. So it will be a little more short answer than kind of the previous exams, although with linear regression, a lot of that is kind of just a function of we're doing a lot of interpretation. I'll ask you to interpret coefficients. I'll ask you maybe to make predictions. We'll kind of go through some of that stuff here. So let's go to practice exam B. And we'll start out with, and I said we can ignore anything where we have kind of squared. We didn't, so I'm not going to expect you to know that. But what I would expect you to know is if we do something like what we have here. Okay. So this is the one that we did in class. So it's kind of nice, and we do kind of hopefully have a little remember doing this. And this is what's on that last individual assignment for your specific variables. But here I've shown you a log model. Okay. So anytime I have a log model, I start to interpret things not as unit changes, but percentage changes. Okay. So here I've got kind of the natural log of weight. And I also took the natural log of height. Right? So typically the way we would interpret these slope coefficients is a 1% increase in height, 1 more inch taller, would predict that weight goes up by whatever our coefficient is pounds, right? The units of the y variable. Well, now, since we've taken the natural log, we basically turn units into percentages. So the interpretation now becomes a 1% increase in height would predict that our y variable changes by whatever our slope coefficient is percent. So in this case, right, our slope coefficient is 1.34 about. So it would be for every additional 1% increase in height, we would expect an individual's weight to go up by about 1.34%. Okay. So that's how we interpret these log models, right? It just basically changes, so unit changes. Now we're thinking about percent changes. Is Ritz ringing a bell, hopefully, right? Now, it's not on here, what might be good to know, is what if I took, excuse me, the natural log of weight, but I just kind of kept my x variable as height, right? So this one gets a little bit trickier. We said, okay, well, now I'm no longer taking the natural log, so I can think about it. It's the effect of a 1 unit change in height, or my x variable. And it would predict that my y variable goes up by whatever that slope coefficient is, except we said when we ever have these log level or level log models, I'm going from units to percentages. So it's not just going to be this coefficient, it's going to be that coefficient times 100, right? So whenever I'm going from a unit change, and I want to translate it into a percentage change, I'm going to have to multiply whatever I see for that coefficient by 100. So let's say, I don't know, this was like 0.12. Right? This is going to be a bad one. This was the actual number. But for every additional inch that height increases, we would expect that weight goes up by 12%, right? Yeah.
Is it log level or level log?
So the way that we name these, right, it's just the way that we would write it. We took the natural log of the y variable. We were still using the levels of the units of the x variable. So there we would have a kind of a log level. Any questions on that? Okay. So what if instead I had, well, first of all, I'll ask you guys. This. What kind of model would I have here? So the y variable is in levels. My x variable is in, yeah, so I've got a level log model. Right? So from here, now the interpretation is a 1% increase in my x variable because I've got my net taking the natural log. That means I should be interpreting that variable as percent changes. Would predict, this is supposed to be a b, would predict that weight changes by not just whatever my slope coefficient is b, but now I'm going from percentages to units. So it's not simply this coefficient, but it's that coefficient divided by 100. Right? So we might see something if we run these if we run these level log models. Let me think. Maybe I see something like 300, right, or something really large. So for every 1% increase in height, weight goes up by 300 pounds. Well, no, right? It doesn't even make any sense. It's every 1% increase in height, it goes up by that divided by 100. So we would say that predicted y variable changes by 3 pounds, right? We have to divide it by 100 before we kind of give that unit interpretation. Okay. So log, everything is in percentages. We don't have to kind of worry about dividing or multiplying by anything. So that's kind of nice. We have a log level model. The original change is units going to percentages. So just like we would with anything else, we multiply by 100 to get that kind of converted to a percent. And then if we have a level log, we're starting with percentages going to units. Well, then we're going to have to divide by 100, right? Or move that decimal 2 places to the left. Questions on that? So that would be a good thing to know, how to make those interpretations of those 4 different models. I said I have 3 here. The 4th one just being level, right? Units. Okay. Which in this one, I didn't give an example, but it would be right. If I had a level model, how would I interpret the coefficient? So weight is equal to this linear regression or this function of height. How would I interpret that coefficient? Well, so I've got a level model. Both my variables are in units. What would a 1 unit change in height be? Being 1 inch taller would predict that my weight changes by whatever the coefficient is pounds, right? Everything's still in units, and it's just kind of our general interpretation there. So the model we started out with, kind of more typical ones are level, right? Everything's in units. So we can kind of convert them. And why would we do that, right? So well, first of all, we can answer a couple other questions that are on here, just that kind of apply to any type of linear regression problem you might see. So if I'm looking at this, can I say at the 95% confidence level or the 5% significance level that there is a relationship between the natural log of weight and the natural log of height? Can I say there's a relationship or no? Okay, let's think about this, right? So we started out with this model, and every single time we run a regression, so we start out assuming that coefficient is 0. Okay. Well, if I can reject this, well, then I'm really saying, if I reject this, I'm saying there is a relationship, right? Because by rejecting the coefficient value of 0, I'm saying I'm rejecting there's no relationship. It's kind of a weird double negative thing, the way we would do this. So what do I need in order to reject? Hopefully this is like burned into our memory going into the exam. For all this hypothesis testing stuff, I need to know if the p-value is less than alpha. If I want the 5% significance level, where's my p-value here? 0.049. So just barely, but yes, I can reject the null or I can reject there's no relationship, or instead say I found evidence there is a relationship. Okay. What if I wanted to say this at the 1% significance level? Well, then I can't, right? Because if my alpha is 0.01, I'm no longer having a p-value that's less than that. The 1% significance level, I can't say there's a relationship between the natural log of height and the natural log of weight. Any questions on that? Yeah.
Can you, going back a little bit, can you re-explain the level of laws? The units, I just.
Yeah. So if I have a level log model, what's the original change? The original change is always on my x variable. So if I've taken the natural log of height, it's going to be if height goes up by 1%. And then it's the effect in units. Well, if I'm going from percentages to kind of like decimal or units, I'm going to have to divide by 100. So a 1% increase in height would change my y variable by whatever that slope coefficient is divided by 100 units. Right?
Okay.
What if I left off the test statistics here? Which should be one of the easiest questions. So you can see the test statistic is almost 2, but how could I reproduce that test statistic if I had left it out? Yeah, so this is somewhere on the formula sheet. It's right here. All it is the coefficient divided by the standard error. So that one, hopefully, I'm trying to, where am I at here? Trying to give you some easy points there by asking you for a test statistic from linear regression output, right? It's just a matter of making sure I'm looking at the right variable, divide that coefficient by the standard error. And that makes about sense, 1.3, 0.67, it's about 2. That's what I end up getting. So the last question, I'm going to add a couple things to it. But the other statistic that we want to focus on across these regressions is the R squared, right? So we said, what's kind of there's several different ways that I've told you can think about the R squared, but how should you be thinking about the R squared? What's an interpretation of it?
What's the higher the R squared, the more accurate it is? Yeah,
so one way we can think about it is it's telling us how accurate our predictions are, right? About this Y variable. So I said one way to think about it is it's like the ratio of your predicted Y's to the actual Y's. The real kind of textbook definition would be it's the the proportion of the variation that we can explain in our Y variable with all the X variables that we've included. We've only used one here, but if we had included multiple ones, it's what proportion of the variation in our Y variable is explained by these variables we use to predict it on the right-hand side, right? Or independent variables. So I'm looking here. It tells me as a proportion, I can always kind of convert it to be easier to talk about in percentages, like it's moving the decimal 2 places. So if I'm explaining the proportion of the variation 0.048, I'm explaining 4.8% of the variation. That's not very high, right? Now, if I was wanting to kind of compare several models to see which one fit the relationship best, so we started out with these levels, that's because we just treat everything like it's a linear relationship. But we said it may not be linear, right? It might be quadratic or have this exponential kind of fit to it. So by doing these different combinations of log, level, we might be more accurately fitting the data as opposed to if we just did like a level model, right? And kind of kept it linear. So when we're looking across models, the way we determine which one's making the most accurate predictions or which one kind of has the best fit for this relationship between X and Y is the one with the highest R squared. So other than kind of using these different, I guess, log level log kind of approaches, trying to fit a non-linear relationship, let's just assume that there is a linear relationship between height and weight for a second. What's one thing that I could do to help make better predictions about what someone's weight is?
Add another variable.
Yeah, maybe add in some behavioral stuff, right? Maybe add in like how active they are, maybe add in their age level, right? That has a huge kind of influence on your metabolic rate and things. So we would want to try to start including as many other control right-hand side or independent variables possible. And that's one way we can increase the R squared. Another way we can increase the R squared other than just kind of changing the type of model we're looking at. Okay. Now, because we did talk about it in class, I wouldn't expect you, but if you gave me an answer, if I left it very open-ended like that, and you told me, oh, I'd actually include a quadratic term, I'd actually accept that, right? I mean, in a way, you're adding an additional variable, but you're also recognizing that even though I'm not going to ask you specific questions about interpreting the coefficients on these square terms, we're somehow trying to use this quadratic formula to pick up on nonlinear relationships, just like we did with these log-log models. Okay. What else do I want to do? Let me think. Okay, here's kind of one I can maybe give you an example of something I might show you. So let's say I run this regression on, looks like my independent or my X variable here is male enrollment. And okay, it tells me up here that Y variable was revenue. So I've got kind of the football revenue from think about maybe D1 universities and then what their male enrollment was. Right? So I run this regression. Just by knowing the male enrollment levels, I'm explaining almost 50% of the variation in the football revenue. Okay? So even just one variable, somewhat predictive. Excuse me. And this is going to be maybe kind of not exactly what you'd expect. But if my enrollment is measured as people, what would my interpretation be? So I've got football revenue measured in dollars, like every additional dollar, and I've got my enrollment as every additional student. So how would I interpret this coefficient? And if you can't see, it's kind of small. It's 2,671. Yeah.
For every this is just level 11, right?
Mm-hmm.
For every one male enrollment, there is about $2,600 increase in revenue.
Yeah, so for every additional male we have enrolled at the university, we would predict that school's revenues go up by about $2,600. Now, going into this, you would ask me that, I probably wouldn't have thought that this coefficient was near as high, right? Because when we have certain variables like this where it's just one additional student, how are they really generating more than a couple $1,000s in revenue? Well, if you think about it, for every additional student, you're getting quite a bit of money in tuition, you're getting state funding, right? So it's not just like this student is going and spending all this money on football games, right? It's that there's additional money coming into the university that is then kind of diverted to those football programs. So you might not expect originally when I asked the question of what's the sign inside, I mean, we would think it's probably positive, right? Having more students in general, let alone male students who may have slightly higher percentage kind of interest in football, right? Not saying that females kind of just saying the percentage would be higher. So we would think there might be a positive relationship. And I would probably think maybe it's small, but I run the regression and sure enough, I see it's actually quite large, right? So we already interpreted that coefficient. We've talked about test statistics, but once again, just the coefficient divided by the standard error. Now, one thing I could ask you, and let me double check, because I think I might have left this. No, it's right here, right? So here on the formula sheet, we've got something that we kind of talked about a little bit, and I said I might expect you to be able to sign some of these things on the exam, which is if I leave off an important variable. So I ran a very naive regression, right? Male enrollment on football, right? Athletic revenue, right? So let's think about writing that out real quick, and then thinking about what bias might exist if we left things off, like I think in the regression down here, just so I have a variable so we've got female enrollment and then men's basketball revenues, right? So let's do kind of men's basketball revenues, just thinking about if I were to add that, or if I was to think about that additional variable, right? So let's say I leave off, actually, I'll give you a different example that might make more sense. Let's do. I'll make it kind of easier because this would be something I would give you an example. So let's think about, I'm leaving out maybe what conferences these universities are in. And I kind of showed you an example where we saw there was pretty significant variation in kind of the revenues earned in different conferences. So let's use the one that I remember from the regression, which was the SEC, which was the greatest, right? Had the highest kind of predicted revenue. So if I'm leaving out this important variable, and these SEC schools all have very large enrollments in general, let alone male enrollments, right? What might be the bias I see in this coefficient? So the estimate that we see, and we'll just give this a number, right? we got one variable, so it's the first coefficient. It'll pick up the actual effect or the actual relationship between the X and Y variable. And then we said plus this additional kind of bias term, right?
What's the example again?
What's what? So what is COV? Between two variables, it goes all really far back. Covariance, right? So that we talked a long time ago, that was like our initial way to kind of pick up if there's a relationship between X and Y, like before linear regression, right? But it just kind of picks up what the relationship is, right? Is it positive? Is it negative, right? We said it's got crazy units and we can't really deal with it. We don't need to worry about that for this. All we care about is the sign. So if we think about, all I'm doing was kind of rewriting this guy right here, okay? So what is this additional bias going to be? Is it going to be positive or negative? Well, we can think through this, right? So here we're just going to replace our variables. We had kind of male enrollment and then whether or not they belonged to the SEC. Right? So I kind of already alluded to this, and I would have to, if I asked you this question, to be honest, as long as you gave me an explanation about why you believe that covariance is what it is, I wouldn't like grade you whether, pull up the data and actually see what that relationship is, but intuitively, like what you would think that relationship is. So you could tell me it's positive, you could tell me it's negative, as long as you kind of state what it is, then I would kind of grade this accordingly, right? Now, in this context, I think intuitively we said, oh, these SEC schools are very large universities. They typically have large male enrollment. So we probably think this covariance is positive, right? So belonging to the SEC, right? Kind of going from the 0 to the 1. More likely that we have higher male enrollment, so probably a positive relationship there. Now, if I had included my variable, my excluded variable, the SEC, into this regression, then you think about, okay, if I had included it, I didn't, but if I had, what would that relationship between being in the SEC and kind of football revenues be? Well, that goes back to the example. We said, what's the highest earning conference? So we would think, this is a positive relationship as well. So I've got a positive times a positive. Variances are always positive. So my bias component here is I might pick up that the effect of having one more male student is whatever the effect is, but plus this additional positive component, which is maybe why I got such a high number there of 2,600, right? Because I might have a really large positive bias there. Now, I can't say anything about the size of the bias, at least from what we've talked about, but all I'm going to expect you to know how to do is, can you put kind of a sign to it, right? Is your prediction going to be too high or too low? If it's positive bias, well, then my estimate will be too high. If this, for some reason, like let's say you told me that you believed, for whatever reason, I don't know, let's say you had a good justification, that male enrollment in SEC schools, there's a negative relationship. Like I just assume that's what you thought going into it. Right. And this could be true. I think that Southern schools typically have higher female enrollments anyway. So, yeah, it could go either way. I don't know without looking at the data. But if I ask you this question, all I need you to tell is give me kind of what you believe the covariance is. You don't have the actual data to prove that, but kind of your intuition going into it. So if you had told me that this was negative, positive times a negative, you would have thought that you actually had a negative bias, that your estimate was actually too low. Okay. Any questions on that? So really the two things you need to kind of sign a bias is the variable that you're leaving out. And I would kind of give you that stated variable, like here, you ran this regression. Well, now think about you left out an important variable, which is blank here, that they belong to the SEC or not. Then what would you expect the bias to be? So kind of signing that covariance, kind of what your intuition would tell you about the relationship between the variable you included and the one that you left out. And then what would the relationship have been if you had included that variable you left out with the Y variable, right? Or what would its slope coefficient been if you had included it? Okay. Any questions on this? So I'll give you one more example of this to maybe hopefully help as you're kind of studying. So let's say we had the same setup. And this is one that we did in class, and I think it's really easy to kind of think about. So we said, what if we just want to pick up the relationship between GPA and being a student athlete? We ran this regression, and we saw, I don't remember what it was something like negative 0.25 or something like that. So we pick up this slope coefficient telling us that, okay, going from the 0 to the 1 group, right? A 1 unit increase in a dummy variable is going from the 0 to the 1 group. So being a student athlete relative to not, we expected GPAs to predict GPAs to be lower, right? By 0.25 points. So let's say I then tell you, but look, we know that at these Division I schools, there's different admission standards for student athletes as opposed to the common athlete, right? They're a little bit more lenient, and they leave out, right? We left out this SAT variable, right? So this SAT variable is going to try to pick up that, excuse me, it's not a perfect measure, but kind of the academic ability of the student. So it might be something we want to control for, but we left it out. So because I left this out, we can kind of put a 1 here, just the variable we left in. I know that potentially, oh, here, what's my I included athlete, and then the one I left out was the SAT score, right? Okay. So if I've got this additional bias component, what is true? Is this estimate too high or too low? Well, it's going to pick up whatever the original kind of effect was, plus this bias component, where what could I probably say is true about the covariance or the relationship between being a student athlete and SAT scores? I said if they're more lenient, well, that would mean that being a student athlete, we would see kind of lower SAT scores there, right? Or we have this negative correlation, right? Or covariance. If I had included SAT into my regression, what do you think would probably be the relationship between SAT and GPAs? We kind of showed they're pretty predictive, right? And it's a standardized test. It's not perfect, but it does kind of have some predictive power. So we would expect that relationship to be positive, that covariance is negative. So my bias would be negative, which would mean that this estimate I saw was actually too low, right? It very well could be the fact, and I think once we started including regressions, we found, oh yeah, the actual relationship is positive, but it was just being masked by this huge negative bias. So if we do include SAT into this, then we eliminate that bias, and we're going to see kind of what the actual effect is. If we've eliminated every single bias, and it gets a little bit more complicated, but that's the idea for what we talked about. Okay. Any questions on this? So kind of know how to sign those biases, know how to interpret those log level log relationships. Those will all be things I might expect you to know how to do on that exam. Yeah.
Can you also brief over and over testing this?
Yeah, I can go through that. I think I only have one example in these, but I might have something on in the folder I can pull up real quick. Before I do that though, I want to make sure that I said anything here. So don't worry about the square. I told you to ignore the squared terms test. Oh, here's a good one. So let's say I instead run a different regression. And don't worry about, I'm not going to make you look up p-values. So here, anything I would ask you is just to reproduce the test physics. I'm not going to make you guys look up p-values. We didn't have time to kind of go into that. So instead, what I might ask you about a question like this is here I've included 3 variables, right? Male, female enrollment, and then men's basketball revenue, right? I think the original I had an idea of like, was there complementarities in these 2 sports or are they substitutes, right? So we could interpret these different coefficients on these variables, but what I might be a little bit more focused on if I have multiple kind of variables on the right hand side is how do I make predictions? Okay? So I've got these estimates. I have these slope coefficient estimates. How could I make predictions for what a school's football revenue is for a hypothetical school, right? So maybe I tell you, I don't know, there's a school with 5,000 males enrolled, 5,000 females enrolled, and what was the other one? The men's basketball revenue is, I don't know, let's do $1 million, right? How would I make predictions for what this university's predicted football revenue or my Y variable would be? Where would I start out? So if I look at this formula sheet, it kind of reminds us of this. But whenever I want to make predictions, all I'm doing is thinking about the y variable that I've got, and I want to make a prediction for it. All I'm going to do is use these estimates that Excel spits out of me for all these coefficients, and then multiply them by whatever that variable, that coefficient went with was. So for the first one, it's just the intercept. So we go back. The intercept here was what? Pretty large. So negative 180.1907. I would then add to that, what, 1582 times however many males this hypothetical school has enrolled, multiply that by 5,000. I would then add into that, well, what's the next variable's coefficient? Negative 131. So I'm adding in a negative here. I guess I should technically probably then just write that as subtracting it, right? So negative 131 times however many female students they have enrolled. And then this last one, 1.69. So 1.69 was the effect of every additional dollar that the basketball team generates. The predicted increase in the revenue, the predicted increase in the revenue the football team earns would go up by about $1.6, right? 1.69. So here, if that's the effect of one, then I think about, well, what if they were spending $1 million on their basketball program? Well, that would be the kind of expected change that we would see in that predicted football revenue. Okay. So making these predictions, all we're doing is taking this linear regression equation that we ran, right? It doesn't matter what the variables are, right? Here they're just x1, x2, all the way to whatever the last variable xn we left or we included is. All these slope coefficients and intercept coefficient estimates, those are those values that you see in the Excel output. So all we're doing is plugging in those coefficient values, and then for all of our variables, multiplying, here it is, that coefficient by whatever that hypothetical kind of, in this case, university, maybe it's a person, right? If we're looking at GPAs, plugging in this hypothetical kind of X value for that variable. Yeah.
So the 5,000 really will be given on that.
Yeah. So I would have to tell you, like, here's this hypothetical university. What would their predicted football revenue be? Yep. Now, the most simplest form of this, which I might have a question on there. Let's say I did run something like this, and I found this to be negative. Oh, actually, no. Let me do a different one. We did this one in class, but it's, let's say we just ran this regression, right? And I said, okay, what would the predicted income, or sorry, predicted GPA be for somebody who got a 1100 on the SAT? Well, this is just an easier version, right? You would plug in whatever value you find for the intercept. You would plug in whatever value you found that slope coefficient, and it's just the intercept. What's that slope coefficient? Times that hypothetical value for that. This one's more complicated. It just has more variables, right? Any questions from that? All right, so what I'll do actually today, I'll have time this afternoon. I apologize, I meant to get this earlier, but I'll clean this practice exam up and kind of get rid of all the questions I don't expect you to answer this afternoon, and then re-upload it. That way you can kind of only focus on the ones that should be relevant. Right? I would also say, looking over that individual assignment, I'll get up a generic kind of answer key to it. So I'll probably choose like my own X and Y variable and then kind of give you an answer key to that, just so you have some additional material there to look at as well. Okay. But I won't post that until after midnight tonight, because you can turn it up to the end of the day. Okay. What else did I want to say here? Let's look up here. I think we kind of went through some of these. These are kind of some more general multiple choice questions of linear regression. Honestly, those will probably be a little bit easier. So kind of notice here, I think we went through these last class. But right, the multiple choice questions you can expect probably to be a little bit more like these naive simple regressions. And then some of the more complicated stuff, the log stuff, kind of making predictions with multiple variables. But a lot more of that, you can expect maybe those short answer questions. Okay. Now, there's one thing that didn't pop up on this practice exam that I want you to know how to do. Two additional things. So one, I'll jump to right away because it's kind of something an example we were just using. So let's say, I've got this GPA variable and I start adding in these little things, but I mainly want to focus on point 4, which is what if I have the SAT variable, but then I also have, what did I have? Being a student athlete. Right? And then I have the interaction of those two things. Okay. So I said we can do continuous variable interactions, but I'll only ever kind of give you these continuous variable and then a dummy variable. Right? We said now we've got two groups, and what we're really thinking about is that maybe not only might there be kind of a difference in where they start out, but maybe there's a difference in their slopes. Right? So if we include this interaction term, we said the way that we think about this is the effect of a 1-point change in our SAT score is going to be different for athletes versus non-athletes. So let's think about the non-athletes first. If I just think about, like, I had some actual values in here for my coefficients, and then when I wanted to make a prediction. Well, if the SAT goes up by 1 unit, that would affect this variable, but it would also affect this guy right here. But if they're a non-athlete, it doesn't matter that this is changing because it's getting multiplied by 0. So for the 0 group or the reference group, the effect of this X variable SAT, the 1 more point on the SAT, would just be whatever that slope coefficient is. Right? But for an athlete, well, this variable is going to go up by 1 unit. So this was our non-athletes. And then if we wanted to think about for athletes, right, it would change this variable. So they're predicting GPA would go up by whatever that coefficient is. But this would change as well. And now it's getting multiplied by a 1. So now when this changes as well, we get added in that additional coefficient on the interaction term. Right? So we said these interaction terms allowed us to pick up the difference between, and I think here, we've got the slope, right, might be different between the two groups. Okay? So what that interaction term coefficient tells me, it's the additional effect of a 1-point increase in my SAT score variable for that group that's 1, or for my student athletes. Okay. I think what was the example? We did a couple examples in class. Let me see if I remember what they were. I think we were looking at like I think I gave you the example of like the male-female beauty thing, right? Where we kind of looked at that. There was a nice kind of visual of it, but that's really how we interpret that interaction terms coefficient, is it's the additional effect of a change in that X variable for whatever the 1 group is, or for whatever our dummy variable 1 group is. Okay. What coefficient up there would tell me the difference in the intercept for these two groups? So how do we think about intercepts? It's kind of where we're hitting at that point where X is equal to 0. We said, in fact, the way we interpret these intercepts, even if we had a variable or a regression where we included multiple variables, was if all the variables were X, the intercept is kind of where that predicted Y value starts out at. So for the kind of non-athletes here, that's just going to be our intercept, right? But for the athlete, what would get added in? Well, SAT score is 0, but when it's a student athlete, this becomes a 1. We would actually get the intercept plus whatever this coefficient is, which here, this coefficient would have to be what? Starting out at a lower point, negative, right? So by including these interaction terms, we also include that dummy variable for whatever group we're interested in. So we're able to pick up kind of differences in that intercept, but also that coefficient on the interaction term tells us the difference in the slopes. Okay. Any questions on that one? So that was problem 4, right? Thinking about interaction terms. The other one was, let's say we did start out with this GPA, then I got some total credit hours, whatever those coefficients are being. we then say, okay, I want to see whether or not, maybe there's some type of preferential treatment, discrimination. We're not really sure exactly, societal kind of issues, but somehow we might think that GPA is varying across kind of genders, right? I think, and then I also have race, right? So we hopefully don't find any, we find really high p values on these variables so that they're insignificant. But if we included them, right? So I had what? White males, white females, non-white males, non-white females. How would I run this regression and how would I interpret one of the coefficients on one of these kind of race gender combinations? Okay. So it gets a little bit tricky. I'm trying to predict GPA still. Let's think about maybe the first group. So had what? White males was my first group. Let's say I included interaction or the indicators for the rest of them as well. In fact, if I included indicators for all four of these different kind of race gender combinations, why would that be a problem? So remember we said, let's say I was wanting to include the level of education and I had an interaction term for like every level. We said we have to make sure we still do one thing when we run that regression. Because the interpretation of our coefficient is if this variable is a 1, so if the individual is a white male relative to the 0 group, well, what's the 0 group? Non-existent person. There is no reference. Well, we have to create a reference group. So we said, what do? We include every single group there. This is what? Non-white male. But we have to leave one of those groups out. Now that group becomes our reference group. So let's say what probably would make more sense in this case is to leave out which of these groups. I'm trying to kind of pick up any type of like maybe discrimination or preference going on. Probably would want to do something like include non-white female, white female, and non-white male. That way the reference is always to the kind of this white male group that I think might be getting preferential treatment. So if that is the case, what would I expect my coefficients to be? If there's, let's say for whatever reason, professors are easier or kind of grading, or maybe there's more resources that white males have available to them, what would I expect the coefficients on each of these dummy variables to be? Negative, right? Now, I'm not saying I don't know what that is. I'm just saying this is an example, right? But this would be a way we could identify kind of whether or not there's racial or kind of gender discrimination going in any context. I think it's probably less likely it plays out through GPAs, but I'm sure there are many other factors we could measure where it does. So the key here is that when you have this group of a group of indicator variables, right? Well, you have to belong to one of these groups based off the way they're defined. Now, I guess we could have a longer discussion about gender, but for the sake of this argument, right? Kind of you would belong in one of these four groups, and so we need to make sure we leave one out. Just like where we had all the conferences for football, we said we need to make sure we leave one out. We have all the education levels, we need to leave out one. We said typically the best thing to do is leave out either what you think is the highest or the kind of lowest group. Excuse me. Any questions on that? So remember, I asked you to do something like this on the exam, and you explain to me this regression, or you write the regression out, like I did here, wouldn't get 100% if you included all four of these, right? Because you have to leave out kind of one of those base groups. Because otherwise we can't interpret the coefficients. There's nothing to compare them to, right? So we have to make sure we leave one out. We said in practice, Excel just drops one for us. But if I'm asked to explain this, I'm kind of expecting you let me know that you're going to have to exclude one of them.
So I was about to ask you want us to then not only leave it out, but then specify that we're leaving that one out on purpose.
Yeah, I mean, if you just left one out, it depends how I phrase the question. If I really wanted to know what the base group is, I would probably phrase it in a way of write out your regression equation. Well, no, if I just asked you to write out the regression equation, you don't have to state what group you're leaving out. I would be able to see like you're leaving out this one group. Now, when it comes to interpreting your coefficient, well, that's going to be inherent that whatever group you left out. Now the coefficient is, will the effect or the kind of predicted change in GPAs from being a non-white female relative to a white male, you have to state what group you left out when you're interpreting the coefficient. So simply asking you to maybe what the regression equation would look like, you don't have to state which one you're leaving out. You're kind of inherently telling me that. But if I then ask you to kind of interpret kind of one of those coefficients, well, that's where you're going to have to mention what your base group was, right? Because this is the effect of belonging to this group, being a non-white female, relative to whatever group you left out.
You just pick one.
Yeah, you can pick any of them, right? Now the interpretation will change a little bit. So notice here, this would be the predicted increase or decrease in GPAs of a non-white female relative to a white male. If instead I had left out non-white male, well, the only difference is this is the effect now of being a non-white female relative to the group I left out, which were non-white males. So it's the only thing that changes, just changes what that kind of reference group is there. But yeah, you could choose any of these and I'll create it accordingly. It's just, there's no right or wrong answer which group to leave out. As long as you interpret the coefficient correctly, it's for whatever one you left
Is
out.
it just that B1 or would that is you interpreting the same way for B2 and B3?
It would be the same thing. It's just these are different groups, right? So now let's go back to the one that makes a little more sense, right? But I left out white males. So now this coefficient interpretation would be the effect of being a white male, sorry, white female relative to a white male. And then this would be the effect of a non-white male relative to a white male. So notice like this, and I would get this granular, but beta 3 would really be telling me about what? Racial discrimination. B2 would really be telling me more about gender, because I'm kind of keeping the race constant, but changing it. And then this one is going to kind of pick up the combination of both of those, right? Or maybe any additional kind of negative effects that are felt by non-white females. Any questions? Other questions? That so you had the ANOVA stuff question, so I want to mention that briefly. I'll just go back to the one that we did last week just to kind of give you a general explanation, which is all I will expect you to know how to do is if I give you this ANOVA output, I just want to know is there variation in respect to this thing that we're measuring, which is BMI, in respect to the rows. So I'm looking at the rows in respect to gender, and then across the columns, with respect to smoking habits. Right? So it's the same idea as linear regression. I start out assuming there's no differences, right? That every single level of smoker has the exact same BMI. If I then find a p-value that's less than alpha, I can say I reject that, or I did find evidence of variation. Now here, we've got very large p-values. No way I'm going to be able to reject the null here. I can't say there's variation in BMI in respect to being a smoker, holding constant someone's gender. And we kind of have to add that additional thing in the right, holding constant the other factor. That was the whole point of ANOVA testing. And then I can't say that there was differences in BMI across gender, holding constant their smoking behavior. So that's the way I would kind of interpret these, whether or not there's variation. Also on the multiple linear regression before we get out, I'm asking you to interpret something where you've got multiple variables on the right-hand side. At the very end of your kind of interpretation of the coefficient, you should always add in holding everything else constant in regression, right? That's the real power of regression. Every other variable we've included there, holding that constant, now what's the effect of this one variable?
So that rows p-value, that's holding the columns constant, correct?
Yeah, so think about when you see the ANOVA testing, rows and column tells you that's what's changing. So this is whether or not there's variation in respect to the rows, holding constant the column. And then the columns tell you, is there variation across the columns, holding constant the rows. So think about it in the ANOVA, like the rows and columns, that represents the variation, the thing that's changing. Okay. All right. Well, I know we got through a lot. I know this is a lot, but if you have any kind of last minute questions or you're kind of finishing that individual assignment or you're studying, I'll be around 2 to 4. I should be in my office close to 2 till 4 today. And then tomorrow I'll be around. So if you have some last minute questions, and you want to meet, shoot me an email. We can kind of set up a time. I'll be around the building most of the day. And just to kind of double check here before I let you guys out, because I don't want to I'll mix up my classes if I don't look at this and I try to do it from memory. So I believe we are Thursday at 9:45. Okay, so it'll be a 2-hour exam. We'll meet here. I'll get that practice exam updated, kind of get rid of those questions I don't expect you to answer. Okay. Oops. All right. Cool. Good luck, Sonny. Like I said, feel free to reach out if you have any questions. We can kind of meet over the next couple of days. I've got some exam Wednesday, but we could also maybe find a time then to meet as well. Okay.